Hi there. So this is Unit 1, Lesson 14, Defining Rotations. Our learning goal is let's rotate shapes precisely. So our warm-up, 14.1, we're comparing angles. So for each figure, which pair of angles appear to be congruent? How could you check? So remember congruent, what does that mean? What do you think it means? A simple way to put it, in between figure 1, which pair of angles seem to be congruent? And if you think immediately that angle ABC is congruent to angle GHL, then you're thinking correctly. Yes, congruent does mean the angles are the same, the length of the line segments are the same, the properties are very much the same, except it's just a different angle. Okay, like a twin. Everything is very much the same, it's just they're two separate identities. All right, figure 2. Which two angles are congruent? Give you some time. All right, so if you saw that this angle right here, right, MZY or YZM, it's a bit less than 90 degrees, whereas these two angles appear to be a little bit greater than 90 degrees. All right, so it'd be these two, yes? Angle LSR and angle KBP, the two on the right. Figure 3, what do you think? All right, and maybe you saw that both the angle DVG and angle XJL or LJX, those appear to be the same type of slices, if you will. So their angles must be congruent compared to the third angle. It's a bit wider. Figure 4, what angle appears to be, let's see, what do you think? Now here they try to make some interesting creations here. What do you think? This one's a bit more interesting. Just look at the angle part. They do throw in some distractors there, don't they? There's a lot of distractors, but we're just looking for the angle. So one thing I noticed is if you just focus on the angle, angle ABC right here in the middle is much greater than 90 degrees. Yeah. Whereas angle DEF and angle GHL appear to be less than 90 degrees. So the first angle here and the third angle over here would look like they'd be congruent. They try to trick us by throwing all these distractors in there and line segments. Don't be fooled. All right, we're going to skip the info gap for now, just for the video time sake, and we'll probably do this at some other junction with our class time. All right, activity 14.3, turning into triangles. So we're going to be using our tools here. Let me zoom out. Label endpoints A, B. Okay, let's do as I say. We have 2 points, A, B. And then they said rotate segment AB clockwise around the center B by 90 degrees. So we're going to rotate. We got A to B. B is on the right, by the way. Okay. And they say rotate by 90 degrees centered at B. So I'm going to center my rotation at B. That's what it would look like if it was 60 degrees, but we're doing 90. There's 90 degrees. Okay, label the new endpoint A prime. Well, this is A prime up here. So instead of down here, it rotated 90 degrees up here. So that's A prime. and use the triangle tool to shade the resulting triangle. So let's see, A, and then to A prime, and then B just went to B prime, which was on the, oh, look at that. Okay, so that is a right triangle, right? It has a 90-degree angle right here. Okay, so that's interesting. It's interesting how a rotation can get you a right triangle. What kind of triangle did we draw? Right triangle. What properties do you notice in the figure? Explain your reasoning. Well, I noticed that AB, right, should be congruent to A prime, B prime. Right? Because the line segment rotated, it preserves rigid motion. That means the line segment is going to be the same length, even after the 90-degree move. It's a right triangle, right? That should have probably gone first. Answer. That's definitely a right triangle. And then what did I notice about the figure? I noticed that AB is the same length as A prime, B prime. Okay. A prime's up here, B prime is right where it was in the beginning with B. All right, let's see. Use the tool below to label the endpoints CD. So we're going to be doing something similar, I think. So here's C. Here's D. They say rotate the segment CD counterclockwise, reverse of a clock, around center D by 30 degrees. Okay, so the right one is D, the right point. We're doing counterclockwise. So here's C. And here's point D. Our center is around D. And counterclockwise 30 degrees. So right now it's 60. We want 30. There we go. Okay, so new point C prime. So C prime's down here now. Okay, it says being C up here. Then they say part B, rotate segment C prime D counterclockwise around D by 30 degrees. Label the new endpoint C double prime. Okay, so we're rotating counterclockwise. We're using C prime to D and around the center D, so we're still here, by 30 degrees. So we're just going to bend this more, 30 degrees. There we go. Okay. Label new point C prime, or C double prime. So C double prime is down here. Okay. Connect C to C double prime. Okay. So let's do that. We have C to C double prime. And then use the triangle tool to shade the resulting triangle. Okay, there's C, here's D, and here's C double prime. Ah, interesting. What kind of triangle did you draw? Is this, what do you think this is? Do you think this is an equilateral triangle? An isosceles triangle? I'm going to leave that up to you. Okay. What other properties do you notice in the figure? Well, I notice that we have a reflection, right? Like if you reflect across, let's see, so there exists a reflection of a right triangle over the line, let's see, what they call it, C prime D, right? Or D prime if you consider that D did a transformation as well, a rotation, but it just stayed where it was. But I'm just going to call it C prime D because that's what they called it. So there's a reflection there. What else do you notice? Is there an angle bisector anywhere? There's an angle bisector of C prime D. Right, so not only is there a line of reflection cutting across for the triangle, it's also an angle bisector, cutting the 60 degrees perfectly. So you have 30 degrees up here, 30 degrees up here, and that's what we did earlier with the angles of rotation. So you had 30 degrees right in that corner, and then you have 30 degrees in that corner as well. All right, so in summary, defining rotations. A rotation is a transformation with a center. So you have to have a center point, okay, somewhere that you're rotating around. An angle, so how much do you rotate around that center? And a direction, are you going counterclockwise or are you going clockwise? All right, that definitely matters. Unless if it's a rotation of 180 degrees, because, well, you're just going halfway around no matter what. Uh, it's like the old saying, a broken clock is right 2 times a day, right? So that's kind of the excuse of the 180 degrees. Here is how a rotation of, so they're giving us an example of the center of point C, right? And that's in the image there, with a certain amount of degrees, T degrees, okay? Counterclockwise, which is reverse, right, of a clock. And they're saying that originally you have point P, but now you're going to point P prime, okay, with the radius of CP. So do you guys see how CP is the same length as C and P prime? All right, that's it. Have a beautiful day.